Our next type is going to be dividing complex numbers with binomial complex numbers in the denominator. So to remind you how to do that, we're going to redo a problem that we've done similar in the past with a radical in the denominator. Again, notice this is a binomial, which means we can't use the method above. So I am going to remind you that what we did in this particular problem to get the radical out of the denominator is we multiplied by its conjugate. The first number stayed the same and the second number changed. Again, you only multiply the conjugate of the denominator to get the denominator to have no radicals. The numerator, you just have to multiply the same thing from the denominator and the numerator. So when I distribute this, I'm getting 16 minus 4 square roots of 5 plus 4 square roots of 5 minus the square root of 25. You probably could have used your difference of squares formula to get this a little bit easier, because you know that these two middle ones will always add to 0, so really you only needed to write the 4 squared minus the square root of 5 squared, which is 5, and that gets me 11. Now that I have that successfully done, I'm going to go back and distribute my numerator, which gets me 12 minus 3 root 5. If there was any factoring I needed to do, I could do that in the numerator. I can factor a 3 out, which gets me 12 minus the square root of 5. But you know what? The 3 and the 11 don't reduce at all. So this is a fine answer, but so is the one right before it, because there wasn't any reducing to be done. So recall that when we multiplied the conjugate of the denominator to the top and the bottom, we got the radical out of the denominator. That is exactly what we just did in that previous problem. Now, this isn't a type of problem for this section, but it does relate to the complex numbers. Now, in order to divide complex numbers with binomial denominators, we are going to multiply the top and the bottom again by the complex conjugate this time. The complex conjugate of 3 plus 5i is 3 minus 5i. Remember, you just take the terms are the same, but the sign in between the term changes. The complex conjugate of negative 8 minus 6i. Now, some students get this one mixed up. The sign in between the two terms is negative, so it's going to change to positive. They usually get that right, but then some students want to make that negative 8 into a positive 8. The sign in the front doesn't actually change, it's just the sign in the middle. So the same as this 3 was positive and this 3 was positive, that didn't change. The only thing that changed was the sign in between. So this negative 8 didn't change, so this negative 8 didn't change. So please be careful when you're deciding what your conjugate is. Now let's remind you, when we multiplied two conjugates, we get, let's see, 9 minus 15i plus 15i minus 25i squared. Notice that those two middle terms cancel out or add to 0. And guess what? They always are going to add to 0. And we have the 25i squared, but don't forget that the I squared is negative 1. And that gets me 9 plus 25, which is 34. So, to verify this one more time, when you multiply two conjugates, you get a real number. Now we need real numbers in the denominator so that we can break it up into a plus bi form. So notice that the answer has no imaginary part, or we say that is real. We can use this to get imaginary parts out of the denominator when we're dividing a complex binomial number. So let's go ahead and try this. On our problem, 2i divided by 3 minus 5i. On this problem, 2i divided by 3 minus 5i. Notice the denominator is a binomial. And because it's a binomial, I have to multiply by something clever so that I get no i's left in the denominator. So what I'm going to do is I'm going to multiply by 3 plus 5i, or the complex conjugate. Now you could use your shortcut because you're multiplying conjugates. Really, it's just a difference of squares. So we can just put the 3 in the first spot and then the 5i in the second spot. Or if you don't like this, you can always multiply it out longhand. That's fine. 3 squared is 9 minus 5i squared is, let's see, that's 25i squared. We know that 25i squared turns into 25 times negative 1, or 9 plus 25, which is 34. Now that I have successfully got the i's out of the denominator, that makes me very happy. I can go back and distribute the numerator, which gets me 6i plus 10i squared. We know that I squareds can be turned into negative 1s. So 6i minus 10. Minus 10, that's a real number. That needs to go in front. So then I want to reduce this into negative 10 over 34 plus 6 over 34i. Now negative 10 over 34 reduces by 2 to negative 5/17, and 6 over 34 reduces by 2 to 3/17 I. And that is my final answer in a plus bi form. So to remind you, if you have a binomial with an imaginary number in the denominator, to get it out of the denominator so that you can write it in a plus bi form, you multiply by the conjugate. Our next problem also has a conjugate in the denominator, so I am going to multiply by its complex conjugate of the denominator. Notice the 5 plus 4i. Notice that the negative 5 will stay negative 5, and the minus and the plus turns into minus 4i. Whatever you do to the denominator, you'll end up doing to the numerator as well. So I could distribute this longhand, but I'm going to go ahead and use my shortcut difference of two squares. I'm going to put the negative 5 in the first parentheses and then the 4i in the second parentheses because I know that this is what it's going to reduce to. So negative 5 squared gets me positive 25, minus, because there's a minus in the formula, 4i squared, that's 16i squared. Now we know that I squareds turned into negative 1, which is 25 plus 16, or 41. Now that I've successfully got the denominator to not have any imaginary numbers in it, now I can go back and distribute the numerator. I can't use a shortcut on this because this is not a conjugate pair in the numerator. I have to do it the long way, so I have negative 15 minus 12i minus 10i minus 8i squared. So negative 15, the 12i and the 10i, that adds to negative 22i. And the I squared I can also turn into a negative 1, which gives me negative 15 minus 22i plus 8. A negative 8 times a negative 1 is a positive 8. I can add my two real parts, negative 15 plus 8, that's negative 7. And now I can split them up into this a plus bi form. The real part would be negative 7 over 41, and the imaginary part would be minus 22 over 41i. If either of those fractions could reduce, you would definitely reduce them, but they can't, so I am done. This is now an a plus bi form, which is equivalent to our original problem, but written in an a plus bi form as a complex number. So this concludes our lesson on complex numbers.